All right, so on with the working of convolutional neural networks. As you will see, the computations that really go on inside of a CNN, they are actually not dramatically complicated, which is clearly good news. However, there is a lot of jargon involved, filters, padding, stride, pooling. These are the terms that you can't avoid when reading papers on convolutional neural networks. So we will clarify on that. And after going through this part of the lecture, you will be confident with these terms and be able to read easily CNN-related papers. Well, but not only read them, hopefully you're also well prepared to put them into practice, which of course we will try and practice in the tutorial. Let's start with a review of some well-known convolutional neural networks for image classification, some well-known models like AlexNet or VGG, which was basically developed by the computer vision group or by a computer vision group at the University of Oxford. These are previous ImageNet winners. And the point I would like to make here just is to remind you that convolutional neural networks exhibit this recurrent architectural pattern, that there are a bunch of computational blocks, convolutional blocks or pooling layers and convolutional layers. And we also see some fully connected layers here. Fully connected means feed-forward neural network. And we always see these layers at the end of a CNN, which makes sense. The fully connected layers are the layers we stack on top of a CNN to perform classification. Any device, any neural network that you build for a classification task will have one or more fully connected layers in the end, followed by a softmax to give you a nice probability distribution over your classes as output. But before that, we have this reoccurring pattern of some convolutional layers and some pooling layers. And we need to make sense of what this is, but what I'm trying to get across here is not that dramatically complicated. Once you understood what is convolution, what is pooling, we can make sense out of this architecture, right? Even now you can make sense out of this architecture. And when we then move on to some other more recent models, here we have ResNet or VGG19, which is the, well, further developed VGG16, obviously. You see basically the same pattern, that there are computational blocks exhibiting a similar type of structure and then repeating each other to give in the end a deep neural network with many multiple layers. A novelty in the scope of ResNet, which did prove successful, that we also see here in the picture are these residual connections, which we have introduced earlier, at least briefly. I was briefly mentioning residual connections in the scope of transformers and state-of-the-art NLP. As said there, residual connections originate in computer vision, and when we have these tremendously deep models with so many layers, and we need to train these models, and we need to backpropagate our gradients all the way from the output layer, where we collect some loss signal, where we can get some gradient signal. We need to backpropagate that all the way, all the many layers back to the input. That's tough. And the residual connections help us achieving that, because gradients can flow easily on the backward path over these residual connections. It's just a copy-paste operations, if you wish. You take the output of one layer, and in addition to feeding this output into the next layer, you also let the output bypass the next layer and then add things up afterwards. And these bypasses, the gradients can easily flow backward during backpropagation over these these connections, these residual connections, and this helps with training these models. But nonetheless, I mean, with ResNet, which was yet a lot deeper than previous models, scholars realized that to train these models, you need to introduce something. You need to do something to make sure these models are still trainable, provided they got so deep. And this is how residual connections have come into play. Other than that, it's just a bunch of convolutional layers, blocks stacked on top of each other, right? So now, finally, let's look into these convolutional layers and what's going on there. The convolution, if you wonder where's this name actually coming from, it's coming from mathematics and more specifically functional analysis, as you can read up on the Wikipedia page or go to Wolfram Math if you wish. It's a mathematical operation of two functions, call them f and g if you wish, to obtain a third function, resulting function, which sort of expresses how the shape of one is modified by the others. Essentially, you shift two functions over one another and see what happens. I don't claim that, unless you have a math background, that this definition is particularly helpful. I did not find it too helpful in the beginning, to be really honest here. But what you might find useful is if you think about a moving average, which you might remember from your econometrics classes and from time series analysis, how you calculate a moving average that slides over your time series and smoothes the temporal development that you have in your time series. That's something like a convolution. So you have one function, or you have your time series, that's one function, and you have your window, your moving average, let's say, of the last three periods that you look at and compute an average over the last three periods. And that window you shift over your time series. So you have the moving average and the time series. This is f and g, or g and f. And the result is then the result of the moving average, the third function, which expresses how the shape of one is modified by the other. That's sort of this moving in the time series analog. But actually, the easiest way is to see how this is implemented in the scope of convolutional layers and see that in the scope of image analysis. So let's do that. That picture you might remember. I used it before to make the point that feed-forward neural networks don't scale for image data. And the reason was that in vanilla feed-forward neural networks, you have your input, which is just the flattened image, x by y times 3, in case that's a color image. And then every unit in the input is connected to every unit in the hidden layer. And that doesn't scale. In a nutshell, what convolutional neural networks do about that, they don't connect every input to every hidden unit. And rather, they do that selectively. You see how we only connect certain input units to hidden units in the picture, unlike in the feed-forward case. And if we carry out these connections selectively, well, obviously, the number of weights that we obtain and need to train in the end will reduce. And depending how selective we are, the number of weights will reduce a lot, or can potentially reduce tremendously. And that gives you an intuition how a convolutional layer, a convolution of CNN, is just a network with convolutional layers. So the key thing we need to look into is a convolutional layer. And this selective connection or connecting of input units to hidden units, that's what's underneath a convolutional layer. A convolutional layer makes use of weights. That's always the case in a neural network. You have weights, you have parameters. And in CNNs, these weights, they have a specific name. We call them filters. I'm sure there is some historical anecdote why we call them filters. Some call them kernels, which is a term that is much more established in statistics. Filters, kernels, all meaning the same thing. It's a bunch of weights, essentially. But that might not be immediately clear. So if you picture it, then you have your image, which is 3D. It's a 3D tensor because we have the color channels for R, G, and B. That's the 3. And then we have the horizontal and the vertical dimension of our image. So an image we can understand as a 3D tensor. And a filter is also a 3D tensor, at least in the scope of convolutional neural networks. It's a 3D tensor. And the 3 is fixed. The dimensionality of a filter is always equivalent to that of the input to which you apply the filter. The 3 is given, but other than that, the 2 dimensions of the filter are parameters. You can decide upon their size. In my example, I assume we start from an image that is 265 by 265. Oh, that's nonsense, I'm sorry. It's 256 by 256. That may be our image. And let's say our filter is 32 by 32. That's, again, it's just a meta parameter. And the filter extends to the full depth of the input image, or as I put it here, the input volume. Volume because the image or images occur as 3D tensors, which is, if you want, you can think of that as a volume. Now, the mathematical operation here, this convolution, that cooks down to computing pairwise multiplication. You have this filter, which is 32 by 32, and you can put it on top of your image. Because it's smaller than the image, you will put it on one part of the image. You put your filter on the part of the image. And for the part of the image, the filter is covering. You sort of have in the image 32 by 32 by 3 pixels, or 32 by 32 pixels times 3 color channels. That's the same size of the filter, which is 32 by 32 by 3. And then you calculate the pairwise multiplication of a pixel and its color channel with the weight in the filter. You multiply this pairwise. And that gives you a single value when you then you add everything up, the result of these pairwise computations you add up, and that gives you one output value. One output value resulting from putting the filter on top of your image at a given position. For this one output value, we can make the point that it's pairwise multiplication. So essentially, we are again calculating dot products here. But since the dimension of our filter is small relative to the dimension of the image, this dot product is relatively cheap. In my example, we have a 32 by 32 filter where the depth dimension is equal to 3 as the source image, which means that we have 32 by 32 by 3, or in other words, 3072 elements over which we calculate the dot product, right? And if you compare that to a feed-forward neural network, well, for a feed-forward neural network, you have this 256 by 256 pixels by 3 color channels. That gives you 100,000 and 96,608, I believe. I have written down the number here. No, I did not work that out in my head. You have these close to 200,000 dimensional dot product, which you need to compute. for each hidden unit. You have these close to 200,000 of weights that go into each of the hidden units in your hidden layer in the feed-forward architecture, because you have close to 200,000 input units. So that's roughly a 200,000 dimensional dot product for the feed-forward neural network. And in the convolutional layer, because our filter is smaller and we put it just on one place over the image, we cook that down to a 3000 dimensional dot product, or 3072. And that's much more scalable, obviously. On the other hand, I mean, we have by now calculated a single output value, 1 point, 1 scala, 1 number, 10 or so. Now, obviously, that does not tell us too much about the underlying image. This filter, however, we can move it. We can slide it over the image. If we slide it over the image, then again, that's a little bit like calculating a moving average. More than a little bit, if you think about it. Just imagine, you have your image. That's my image here. I hope you can see that. So I take my filter, I put it to the upper left corner of my image, and it will cover a part of 32 by 32 pixel in that image, if that happens to be the size of my filter. We don't have to worry about the 3 color channels, because we said the depth dimension of the filter is always equivalent to that of the input image. Things always work out there. So I put my filter on the left upper corner of my image. I go through this pairwise multiplication, and it gives me 1 point as output. And then I can slide my filter over the image, right? And with every step with which I slide my filter over the image, maybe I shift the filter by 1 column. We have some examples later on. If you wonder, you don't have to follow all my hands and what's trying to go on here. We can obtain multiple outputs because we slide our filter over the image, and for every position where we put it, it contributes 1 output volume, and then we slide it over the image to gather multiple output values, which is what I'm trying to also show you on the slide. And the result we can then call a feature map. There we can call a feature map. And if we slide our filter image and then move it down by 1 row and slide it again over the full image and move it down by 1 row, slide it down over the full image, eventually we get this filter map. Sorry, we get this feature map where we have a depth dimension of 1 because we were using 1 filter. From 3, we reduce the depth to 1. From depth of 3 in the source image, for the 3 color channel, we have reduced the depth to 1. And from the resolution of the image, this 256 by 256, we reduced the resolution to 225 to 225. If you can't make sense out of these numbers, no worry, we're going to get there. Just note the image resolution is reduced after the filtering. That we detail later. For now, let's note that each of these output values that we collect in our feature map follows from this element-wise multiplication and adding up results. And this is a very well-known equation that we see here, where we have W times X plus some bias, a linear equation. This is how the values in the feature map are calculated when we put the filter on a position in our image. X is the data in the image, which is a 3D tensor of the same size as the filter. W, our weight matrix, that actually is the filter, which also which has the same dimension. So we calculate the dot product, and then we add a bias. And B here is just the scalar value. So the filter, that really is the equivalent of our weight matrices. Or that is our weight. The filter is the weight. If our filter is 32 by 32 by 3, we have these 3072 weights within that filter. And with these weights, we carry out this linear computation, x times w. And the specific value of these 3072 weights, well, we need to train them. We initialize them randomly and train the network using backpropagation. Nothing new here. It looks much different from a feed-forward neural network, I know, but it's not that different after all. We still have this input times weight plus intercept, right? Very same thing. Just that we don't consider a fully connected layer anymore, but use this convolutional layer where we have a filter that's smaller in size and that we shift over the image. Earlier I said we connect inputs selectively. That was the intuition I was providing you. Let me go back there. Here. That was the intuition. We collect input to hidden units selectively. And the purpose again was to give you an intuition. And now you know, well, that's not 100% accurate. It's just an intuition. It's not that we connect inputs selectively, and it is not that, well, or normally, it is not that certain input units are left out. In this picture here, for example, this input unit and that input unit, they are left out. I was saying we connect selectively. Are they left out? Do we have parts in an image that we ignore? And if so, which parts are these? It's not really that we leave out inputs, that we skip over inputs. Rather, we reduce the number of weights that we consider. That is the filter, which is smaller, 32 by 32 in my example. We reduce the number of weights and then let all the inputs share these weights. We just have that many weights. We just have these 3072 weights in our filter. And by sliding the filter over the image, we sort of share the weights for all the input units of the full image. That's the idea. And we can call that convolving. So the weights are shared and don't change when we slide the filters over the image, when we convolve over the image. This is how they call that. We let the filter convolve over the image. Well, this was well, for me, I learned a new term here, convolve. Haven't used that much before in my English speaking. That's how they call that. This is the technical term for this operation here. More rigorous than saying we move the filter over the image, but that's what we do. And well, so far we used one filter. And now you might wonder whether if we had roughly 200,000 weights in a feed-forward neural network, and now we use only 3072 weights, that's a lot less. Do these weights give us enough flexibility? Do they offer us enough expressive power in order to really learn what's going on in the image, to make sense out of these image? Is the expressional capacity of our neural network big enough if we just have this single filter? And the answer is no, it isn't. That's not enough. However, we don't have to stick to a single filter. We can have more than that. It's just a weight matrix, essentially. We can have more. We can have as many as we like. We can scale things up. Of course, then we have multiple weights and complicate the training. So we would not want to have so many filters that we end up with close to 200,000 individual weights. If we are ready to tune these 200,000 weights, we could equally use the feed-forward neural network, right? Still, the number of filters that we use is a metaparameter that we need to set when we configure a convolutional layer. Very much as you having to set the number of hidden units in a hidden layer when you configure a feed-forward neural network. It's the same idea. We have metaparameters, and when we design a neural network architecture, we have to make a decision on these metaparameters. Same with CNNs. The number of filters is one important metaparameter. In convolutional layers, they use multiple filters. We see here, for example, that I could consider using 4 filters, all of the same size, 32 by 32 by 3. But the 3, it's important to remember that the 3 is given. The 3 is not part of my decision making. The 3 is given. And if we apply these 4 filters, we end up with 4 feature maps, 1 per filter. And what you see here is that we could stack these feature maps. We can stack these feature maps on top of one another, and then the depth dimension of our output, the third dimension in our tensor, is 4. The number of filters is a metaparameter. Depending how we set this metaparameter, we implicitly also set the depth dimension of our output tensor. So the convolutional layer performs an operation on tensors. We feed in a tensor, we get out a tensor. But in image processing is often being an understatement, is often a 3D tensor that we feed in, and then we get an ND tensor out, with N denoting the number of filters that we opt for. Input-output mapping for tensors, that's what it is. But it doesn't have to be 3D. We can consider a simplified example. Here is a simplified example. I get rid of the depth dimension in the input image. This gives me a 2D example, or an example in 2D, where we could say, we have a black and white image. Black and white is nice because we don't need to worry too much about the numbers. We have as many pixels as our image is, the number of pixels is given by the resolution of our image. For simplicity, I'm assuming that to be 9 by 9. So we have 81 pixels arranged in this 9 by 9 matrix, and black and white, so every pixel can only be of 2 states, either it's black or it's white. If my input is 2D, my filter is also 2D. Remember, the depth dimension of the input determines that of my filter. Remember as well, filters tend to be smaller, so if my source image is 9 by 9, my filter is, for example, 3 by 3. It's just weights. And for simplicity, a weight is normally a real number. Let's say the numbers that I have in my filter, this is just for our illustration, are also 0 to, from +1 to -1, or I will use only the values 1 or -1. But again, that's only for simplicity. Normally, the weights in our filters could be any real number. But my focus here is the convolution. So let us convolve this filter over our image. We start in the upper left corner. And this is then to illustrate, right? I said we compute a dot product. We compute basically the pairwise, the element-wise multiplication of the values associated with our pixels on the source image and the weights that we currently see in our filter. The weights are, well, initialized, maybe randomly, and then they are trained. So the filter has weights, which are trained. And after training, let's say we found this filter here. You see the calculations, maybe some highlighting. If we go through that, so this one here in our filter is that one, just that you can orientate the self. That's this -1, and that's this one, right? And conversely, and that should be enough. Here we have -1 and -1 and -1, and this is what you see here, -1, -1, and -1. So pairwise multiplication. I'm making a big deal out of what a pairwise multiplication is, don't I? Sorry. Maybe this is why my videos get so long. We do that for the whole filter, and then we add up the results. So we add up here our filter results and obtain a value of 3. And the value of 3 is our first result. And then we slide the filter. So when I said before we could move it by one column, I was having this picture in my mind where an image is essentially a matrix or a tensor. But here we have only 2D, so it's a matrix. And then we can move our filter by one column. The image part that's now covered by our filter has changed. The pixel carry different values. And then if we do the convolution, if we carry out this pairwise multiplication, we also obtain a different output value, which happens to be -5 in this example. And you can convince yourself whether this is true. It's a trivial exercise. And then we go on. We move the filter by one more column. Since we have new source data from the new part of the image that's now covered, the filter is always the same, weight sharing. This is weight sharing. The weights of the filters, the values in the filter, they do not change at all. Yeah, and that's it really. That's the operation in the convolutional layer. We just continue in this way and create our feature map. Once we shifted the filter over the first row, we move it downwards, and this is basically how we complete our feature map. And well, yeah, this looks interesting, or maybe not. It's just a bunch of numbers that we get. But if you, well, I did that in Excel. If you then use Excel functions to color code that, actually, you see a pattern, which you couldn't see before. You see this pattern of the cross. Clearly here you have, what's my color? Let me use purple. Right here we have this. This is a very prominent pattern that we see. And also, of course, this is apparent, and so is this. This characteristic, I wonder why I color-coded the picture when I color-coded again. Well, it highlights things a little bit. This characteristic cross image, that we got out. And that signals or sketches the idea how by this filtering we can detect low-level patterns. Revisiting my filter again, yes, indeed, it's like a cross-detecting filter, isn't it? So this filter, by the way it was trained, remember, of course, this one I made up, but normally these get trained. They are trained to detect certain patterns in the data, in my image, like a cross. And to convince you that that's really the case, let's use a different filter. Here we have a filter, well, that's like a filter to detect Mander organelles in matrices, right? You could think of it as a filter for detecting main diagonals. And if you run that filter over the image, this is the result that you get, and it worked out very nicely. You have this main diagonal nicely highlighted with large numbers, and off-diagonal elements are, well, not that large in number. And this is what we call a pattern. Doing that once more, for the off-diagonal element, we can construct yet another feature map. And now we have 3 of these that we can stack on top of each other. Then our output tensor would be 7 by 7 by 3. If we now move on, and that's it, almost. Minor adjustment. We don't stick to the linear operations in CNNs normally, but introduce an activation function to inject nonlinearity in these feature maps. So if we calculate the ReLU activation, for example, of that feature map, you can convince yourself that the core pattern is really carved out even more clearly, and this off-diagonal is now even more apparent. Easy, isn't it? I was promising you that the computation and the convolutional layer are not too difficult, and I think you agree with me. That's not rocket science. That was our 2D example, and it is to, well, just further elaborate on what we had before. We have seen how we can construct this 7 by 7 by 3 feature map from our input data, from our source image, by applying 3 filters of size 3 by 3 each. That's really the essence of the convolutional layer. At some point, I felt a little bit playful, and noting that my previous example and the lecture were often a bit geared towards boy, using cars and transformers and etc. And sometimes I got some critic at home where my daughter was a bit critical with me for all these examples. So I thought I need to do something about that. And here's a beautiful picture of a little unicorn. My daughter is very much into unicorns, by the way. And I wanted to examine and demonstrate to her, no, not to her, the ability of convolutional layers to really detect low-level patterns. So if we, well, got rid of the coloring, that would make it too difficult. That's our black and white image. And look how this looks like when you encode the unicorn in Excel. That's our black and white unicorn with 32 by 32 resolution. And then I was applying this little filter here. That's actually, not sure you realize that, but that is a unicorn detection filter, right? And if you look at the output image, indeed, well done. The filter did its job. It got us the pattern that there at the top of the head, there is our unicorn. Beautiful. And well, what other patterns stick out in this image? Well, here is a horseshoe filter. And if you apply this horseshoe filter to our image, look there. Yeah, indeed. We learn that our unicorn, well, we kind of learn that our unicorn actually has 4 horseshoes. Beautiful. So you are really able to detect low-level patterns with convolutional filters. There's one thing. If you followed along carefully, you will have noticed that the resolution of our image shrinks through the filtering. And if you also remember that convolutional networks tend to be really deep, then that doesn't go together too well. If we shrink the image resolution with every filter and make that many times, the image would basically shrink to 0 quite quickly. This is an example. Maybe the numbers do not make immediately sense to you. We'll introduce some equations in a minute. But you have seen before, well, just in the example of this cross or in the example of the unicorn, we had the 9 by 9 input dimension, and then we had the 7 by 7 output dimension. You have seen this decrease in the dimensionality. And if, for example, you would have a 32 by 32 image and you apply a 5 by 5 filter to that image, the output dimension would be 28 by 28. And then the depth dimension would be equivalent to the number of filters that you apply. Right? This is always the case here. This 3 triggers that 3. And this 6 triggers that 6. And this 6 triggers that 6. While this 10 triggers that 10. Where the number of filters is a metaparameter of the convolutional layer. And then, okay, from the 28 by 28 image applying our 5 by 5 filter, we cook it down to a 24 by 24 image. And you can easily see how this would continue and shrink the image to 0 at some point, which is undesirable because we want these models to be deep. This is where padding comes into play. You can actually calculate the output dimension of your image. It's not rocket science. Here you see how you do that. Noting that it's your choice how you move the filter over the image. I was before assuming always that you do that in this 2D examples, you do that column by column. From left to right, you move things one column down, one row downward, and then again from left to right, and another row downward and left to right. That was my assumption. But you don't have to do it like that. And the parameter stride, which is yet a novel metaparameter, governs how you move the filter over the image. And you can, it helps, at least it helps me, to think about that really by picturing a matrix as here, where then we could say, yeah, the stride is the number of columns by which we move our filter. And if our filter has some dimension, f, and if our image has some or f by f, and our image has some dimension n by n, then we can calculate the output dimension as n minus f over the stride plus 1, which would give the values we have seen before, how the 32 by 32 image came down to a 28 by 28 feature map, always ignoring the depth dimension, because that's not our concern, as we've seen before. That's sort of governed or follows by the choice of other metaparameters, let's say. Yeah, so if the stride is equal to 1, then we have essentially 32 minus 5 plus 1, right? And that is 28, isn't it? That makes sense. So here it works out. And on the other hand, say we set the stride equal to 3. Then this is basically our first output. And then we shifted 3 columns. So that would be our next. And here is one more, right? So we basically have 3 outputs here in that dimension. So we have 32 minus 5, 27 divided by 3, which is our stride. That's 9 plus 1 is equal to 10. So we will end up with this 10 by 10 image if we carry on like that. Okay, well, that's nice, but this is just to show, okay, images do reduce in size, and hey, you know what? We can calculate how much they reduce. Wonderful, but we haven't really overcome our problem. And to overcome our problem, we introduce padding, or zero padding to be precise. meaning that we just augment our image data with a frame of values that are all 0. And if these values are all 0, then obviously in this element-wise multiplication, their effect will be, should we say, neglectable. And then, well, our equation, we change it a little bit. We add to the input dimension our padding, which is yet another meta parameter. How much do we pad? How thick is the border of zeros that we introduce around our image, right? So with a 1 pixel border, we would basically have 9, which is the dimensionality of our input image, 9 by 9. And with a pixel border of 1, we then have 9 plus 2 minus 3, which is our filter dimension, over the stride plus 1. And this way, you can ensure that the feature map that you compute through the filtering or through convolving the filters over the input volume don't shrink the input volume. Or at least, or maybe they do shrink the input volume, but you have full control over this resolution of the image. And that gave rise to some very common settings for these metaparameters, that when you have a filter which is f by f, and you set f to 3, for 3 by 3 filters, you would typically pad with 1, and for 5 by 5 filters, you use 0 padding with a pad value of 2, and for filters that are 7 by 7, you would use 0 padding with a value of 3, and you can convince yourself that when you choose your filters in that way, of, well, this filter size and the corresponding padding size, that the resolution of your feature map will be the same of that of your source image, minus the depth dimension, but the depth dimension you control anyway by selecting as many filters as you wish. That is the idea. So in this example here, we have a 9 by 9 image. We apply a 3 by 3 filter. Since our filter is 3 by 3, this guideline suggests us that we 0 pad with a value of 1. So we have 9 minus plus 2 minus 3. And guess what? The output of that formula really is 9. Our output dimension is 9 by 9. Summing up, we have a bunch of metaparameters, which are the number of filters, call it K, the stride of these filters, call it S, the spatial extent of the filters, which we called F before, and the amount of 0 padding that we add, which is P. Well, setting metaparameters is always delicate. In conventional machine learning, it's often done by model selection. In business analytics and data science, we've seen grid search in action. Earlier lectures briefly introduced random search as a maybe possible vehicle for tuning metaparameters in the scope of deep networks. But as typically in the scope of these networks, also with CNN, the overall number of metaparameters is just excessive. And therefore, a full tuning of all these metaparameters is typically infeasible. And especially these here are often set more by expertise or by following standards. You have seen before how the parameter P, the padding, follows certain standards. And also for the filters, these sizes, 3 by 3, 5 by 5, 7 by 7, are commonly encountered. So these parameters are often just set by either having your own expertise or by following what you read in other image processing papers. What else? Convolutional layers then receive an input tensor, W by H by D, and they transform this into an output tensor, which is W2 by W by H2 by W, what's wrong with me? W2 by H2 by D2. And we've seen how we can calculate the output dimensions. And previously, I was, for simplicity, assuming that my images are always rectangular, 9 by 9, 7 by 7, 32 by 32. I don't have to assume that. In general, we can calculate the output dimension as W equals W1 input width minus my filter dimension plus 2p, the padding, over the stride plus 1. And the same is true for the horizontal dimension, where we calculate values accordingly. Filters are typically rectangular. If you think about it, there is little need, at least I don't see any, to have filters that are not rectangular. So we do not need F1 and F2 here or something like that. The filter is typically just rectangular, which is fine. And then the parameter D2, the depth dimension of the output, is equivalent to the number of filters that we pick, that is K. And then we can also note once more that the number of free parameters that we introduce in a convolutional layer is given by these filters, which are f by f times d1, the depth of the input, just before the convolutional layer. So we have f by f by d1 times the number of filters k, weights, plus another k biases that we also consider as parameters. And that's under our control and a lot less compared to the feed-forward case. Well, provided we use our control carefully and wisely and don't make the filters too big and use too many of them. And then we obtain our output tensor, where we hope that the feature maps capture the important patterns in our output tensors. And to that end, certainly we need to train these weights. That is, we need to train these filters. And then hope that backpropagation will just give us the filters that we need to make sense of the images. That backpropagation will eventually give us this horseshoe filter, or the unicorn filter, or the cross or diagonal filter, which I just used because for illustration, normally these follow from backpropagation, or they follow from the training of the CNN. CNN also exhibit pooling layers, at least occasionally. If we use padding to avoid our image resolution to shrink too quickly, at some point, maybe we want to shrink the image dimension for reducing the number of parameters, speeding up the training, and encouraging this idea that we learn latent features that we can aggregate, and then at some point we don't need that many weights anymore because our latent features are already quite powerful and we don't need so many of them. And that's basically what pooling is about. There are different forms of pooling, as we shall see shortly, and they always reduce the resolution of the image. So if we have a convolutional block where the output tensor is 256 by 256 by 64, we could use a pooling layer in order to cook that down to 128 by 128 by 64. Again, we don't touch the depth as with the convolutional layer. Pooling layers don't touch the depth or the third dimension of the tensor. It's all about the resolution of the first two dimensions, horizontal, vertical dimensions, and there we can cook down using max pooling, which is a common approach, or average or global pooling. This example tells you in one picture what pooling is about. It's the same as filtering. essentially. It's like applying a filter, just that this filter has not a weight. There are no weights involved. There is just one mathematical function, which is the maximum or the average. Well, could in theory be the minimum, but that's not used. And then you apply this mathematical function, you apply this aggregation function to the part of the image that you cover. And in this example here, we have our 2D matrix. And then if you imagine a 2x2 filter with a stride of 2 and max pooling, that means that the first part of the image that you cover, right? Why do I call it? So you put the filter here. Strictly, it's not a filter. It's kind of filter. You put it here over that part, and then you apply the max operation, so you find the 6. And that's the 6, right? Easy. Colors show us what's going on here. But you could also average over the numbers. That would be average pooling. And then deciding on the size of this pooling filter and the stride, you can control the output dimension as you could before. Same equations here. Also emphasizes that this is just filtering. Earlier neural networks or earlier CNNs made use of pooling, and we can go back to the picture of the architecture of the earlier ones. AlexNet, for instance, now you can really make sense of that. So we have a convolutional layer, and then another one to process the output tensor of the first convolutional layer, and then we do pooling to reduce the image in size. And then we have another convolutional layer, and the output tensor that we get from that one, we pool again to reduce the size. And then 2 fully connected layers, softmax on top, that was AlexNet. Yay, hey. 10 years back, you could have won the ImageNet challenge with that type of network. Nowadays, you couldn't. And you see the same pattern in VGG or VGG 16, which should have 16 layers, depending how you calculate, but I guess this is why they called it VGG 16. Very same pattern. However, if you look at ResNet, where's pooling? You really have to look hard. Eventually, you will see it. ResNet, okay, we have one pooling here, where if you look very carefully, you see it's pool over 3, so basically pool over 2, I'm sorry. So you basically sort of half, I think this is what it means here, the resolution, and you have another average pooling right at the end because you start with your fully connected layers. And in VGG19, okay, here there is a bit more. We have here 2 pooling layers, and here is another pooling layer, and here is a pooling layer. And if you wonder, no, there is no reason why I draw that as a corrupted sine curve. That makes use of pooling a bit more intensively than ResNet, but we can make the point that state-of-the-art image nets use pooling sparsely. And it makes perfect sense because, I mean, what's the point of pooling? You want to reduce the dimensionality of your input tensor, reducing weights, simplifying the training, etc. That's why you reduce the dimensionality, also fighting overfitting a little bit. That's the point. And you do that by applying this aggregation function and then saying, well, you know, in this part of my feature map, I just take out the biggest value, and that's it. I reduce the part of my feature map to the maximum value. Fair enough. But if the point is to reduce the resolution of your image, as we have seen before, you can achieve the same thing just by deciding on the amount of padding that you add. It's a bit bizarre if you think about it. We started with convolutional layers, and then we learned that they would reduce the dimensionality of the image, and then we introduced pooling to overcome that reduction of the resolution of the image, to not shrink it too harshly and too quickly. But you can let go on padding, and then you reduce the dimensionality of your image as much as you want and when you want it, and you don't really need pooling. And this is why pooling is not used that often in state-of-the-art nets anymore. You don't really need it. And it's I cannot tell with certainty, but looking at this architecture here, where you have some pooling layer very early before you start with these recurrent convolutional blocks, and then you have one right before you start with the fully connected layer. I would imagine that follows from experimentation, where you try out different things, and where you then say, well, at the heart of the computations, I don't really need pooling. If I want to reduce the dimensionality, I just set my padding accordingly or let go on padding entirely. And that's probably how they came up with these type of architectures. So we had pooling, we had padding and stride, and most importantly, we had the filters that convolve over the image to create the feature maps. Guess what? That's it. That is CNN. They use these core operations, and they do that consecutively and many times. That's a picture I took from the MATLAB documentation. Very nice way to put it, and really highlighting these core operations. We have the input image, then we do convolutions with ReLU activations typically. We can use pooling to shrink the size, another layer of convolutions with ReLU activations, another layer of pooling, etc., 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 etc. And this way we create these feature maps, and that is basically how we extract latent features from our images, or more generally from our input tensors. And CNNs really serve as a feature extractor. The output of these convolutional blocks is a tensor. That's not readily useful. You need to do something with that, and to that end, you would normally just stack some other layers on top of your architecture to translate these features into forecasts, or just to do something with these features or based on these features. Using the terminology of previous lectures, you have a downstream application, and then you stack a neural network on top of your CNN layers that is geared toward your downstream application. In the simplest case, your downstream application is classification. So you put a bunch of fully connected layers on top of your CNN with a softmax in the end to get a nice probability distribution over classes. That is the go-to approach for image classification. That is how you approach image classification in 2020, and it's probably all you need to do image classification. Many applications need more than that, but that's a different story. Yeah, and note this similarity to our last NLP session. We have the CNN part, and then we put something on top of it to solve some downstream task. This is exactly how BERT works, or other state-of-the-art NLP models. The last layers in the architecture are geared toward the target task. Also think about my brief excursus into the world of GPT, where you basically put some layers on top of your base model for the downstream task, and where you would pre-train the base model with all its many layers to be generally useful. So it's exactly the same in image processing, just there it was invented first. So the CNN idea with the feature extraction part, which is the CNN part, and then layers stacked on top of that for the downstream application that originated in image classification and computer vision. And then it was basically brought into the world of NLP. We just covered it in the different order in the lecture. And if you would like to make some comments, I'd appreciate comments whether you think it's actually good to do it in this order or whether in retrospect you would rather have the CNN part before we look into NLP. It's a question I have in my mind. Obviously, there are arguments for both ways. I would be interested in your opinions. Feel free to share it on Moodle if you want to make a comment. Another thing that resembles NLP is transfer learning, because if you want to train a CNN from scratch, good luck. Good luck with that. You better be Google or Facebook. Otherwise, you'll probably won't make it because the computational cost is so large. When you work with images, that's really a lot of data. You need much memory, much processing power, GPUs, TPUs, right? That's not going to work. But luckily, transfer learning allows us to not have to invest this computational effort. We just use a pre-trained network. Many of these are available. You can download. There's ResNet. You can download AlexNet. You can download VGG 16 and probably 19 as well. You can download all these models that were trained on ImageNet. I put use a pre-trained network, e.g. ImageNet, on my slide. Well, in NLP, there are a set of corpora that you wouldn't use in order to pre-train your models. Google News embedding, there is the Wikipedia corpus, there are other corpora. In computer vision, that's not really the case. There is ImageNet, and that's the go-to database, right? So all the image models that you can use are pre-trained on ImageNet, I believe. At least those that are publicly available. And then you fine-tune them on your image data set for your downstream application. You fine-tune the weights, probably selectively, because in a deep CNN you will have many weights, and if you train all of these weights, high computational effort, the risk of catastrophic forgetting, maybe, remember the Ulmfeld lecture. I guess you want to fine-tune your weights selectively, but honestly, I guess that I'm not that experienced when it comes to image processing, image modeling. Haven't been involved in any projects where we really develop production-ready image model. Haven't been involved there, so take that with a grain of salt. But clearly, if you fine-tune all the weights, you must be ready to cope with the computational costs that you invest here. Right. And in that case, if people gossip about all these deep neural networks being able to do nothing but distinguishing cat from dogs, sometimes you hear this critic. It's a famous case indeed, and for those who are not enlightened, it might be a bit bizarre why focusing on that case, why distinguishing cat from dogs, distinguishing that is good for nothing. Okay. But actually what's been done here is you just pre-train models to detect general patterns in data using ImageNet, and then together with a little bit of fine-tuning. And really, often you only need a little bit of fine-tuning and don't need to fine-tune that much. You can get very good image classification models for your downstream tasks, which could, although being pre-trained on dogs versus cat, help you to classify images of dinosaurs or whatever you might be interested. And that was it with image analysis. compared to the NLP part, it's much more foundational. There's much more new stuff going on in the field. But again, not entirely sure that it's of immediate use for economic applications, or better put, in relation to text data and NLP, I believe we as economists or business and management people are closer to text data, and therefore text was my focus. And hence, the last part of the lecture will be on CNNs for non-image data. And guess what? There we will also have some text data.